Now see, in this question they have given, consider a certain hydraulic control system will have some control system where the input is the reference fluid flow Rs. Input they have given by Rs and output they have denoted by Ys, right? So if I draw the diagram, there is certain input that is Rs and there is certain output of the control system that is denoted by Ys. Next they said it is used under PID controller in a parallel form. So remember I told you, then will have error, then we'll use controller, right? All are in the parallel form. Basically here the error is there. And then we'll have plant. So this is for KP, KI and KD, right? Now they said the hydraulic process is described by the function GS as shown below. So this is for the PID controller they have given, and this is the GS function. GS is 10 divided by S plus 1 ka whole square, and GPID is given as KP 1 plus 1 by tau I S plus tau ds, right? Now they have given us the value of tau I, that is 0.25, and tau d, that is 0.1. They have given mention in the question, right? So just substitute that value and calculate the transfer function of that. If I'll redraw the block diagram, then the block diagram will be like this: an error detector, GPID controller, right? Then GS for the plant, right? Then in that case no feedback is given, so we can consider feedback as 1, right? So this is Rs. If we want to calculate the transfer function, that would be output divided by input, right? So if I'll combine it, I can denote it by G dash S is equal to GS multiplied by GPID, right? Because they are in series. And if the blocks are in series, then in that case it would be multiplied, correct? So that would be G dash S divided by 1 plus G dash S multiplied by HS. HS is 1. So in this case, G PID is given, this one. If I substitute the value, then it would be KP 1 plus 0.25 S plus tau d is 0.1, so 0.1 S. Okay, this one is given, this one is given, and GS is also given. Now substitute it, then tell me the final answer. So after calculation of transfer function, we'll get this value. Okay. Now see, they have asked you the calculate in transfer function. Next they have asked you calculate the value of critical gain K critical when the system is marginally stable and when Kp is equal to Kc. Okay. So whenever you need to calculate the value of K, you need to do it for the Routh-Hurwitz. And for the Routh-Hurwitz, we need characteristic equation, right? So if I'll solve this, this would be the characteristic equation. So open the bracket and make it in a standard form like S cube, S square, then S, and then Kp. Then tell me the proper characteristic equation which you got it from this. Okay. Then after getting characteristic equation, we'll use Routh-Hurwitz criteria to calculate the value for Kp. Understood? After solving this characteristic equation, we'll get this characteristic equation. Okay, s cube, s square, s and s0. Now we need to calculate the value of kp, and we can do it by using Routh-Hurwitz formula. Do it and then tell me the value. Now see, s1 you got it this one, s0 you got it this one. As they said in the system that the system is marginally stable. Okay, if they said system is stable, then all the columns of the first column terms would be greater than 0. Now instead of saying the stable, they said marginally stable, right? If it is marginally stable, then equal to 0. If it is unstable, then it would be less than 0. Okay, so if I'll solve it, 10 kp 2 plus kp minus 40 kp divided by 2 plus kp would be equal to 0 because it is marginally stable. So this into this is 0. 10 kp means 20 kp plus kp square minus 40 kp is equal to 0. So kp square minus 20 kp is equal to 0. So kp minus 20 is equal to 0. Kp value would be equal to 20. Okay. Now they said for the marginally stable, if the system is marginally stable, for marginally stable, system would be marginally stable only and only if kp value is equal to 20, right? Okay. Now back to the question. In this, they said when kp is equal to k critical, we need to calculate the frequency also, right? So see how we can do it. For oscillation of frequency, we'll get this thing na 2 plus kp s square plus 40 kp is equal to 0. How did we get it? From this equation. Okay, remember the auxiliary equation you have done in the root locus? We'll do it like this na 2 plus kp into s square plus 40 kp into s0, right? Then in that case we know kp is equal to 20. We can substitute the value of kp as 20, right? It is s square. So from after substituting the value of kp, can we get the value for s? Tell me what would be the value. So we'll have 2 plus 20 s square plus 40 into 20 is equal to 0. So that would be 22 into s square plus 4 to 8, 800 is equal to 0. S square will be equal to minus 800 by 22, right? So it would be plus minus root of 400 divided by 11. That we got it as omega. That is in radian per second. Now you can solve it further. Now after getting the value for s, let's see what we need to calculate in the next part. They said determine the range of the proportional controller gain kp for a safe stable operation of the closed loop system, right? So see, as what we got kp is equal to 2. As I told you, whenever we'll have equal to, it means at kp equal to 2 the system is marginally stable. Okay, if we'll have kp greater than 2, then the system is unstable. And if we'll have the range of kp vary from 0 to 2, then the system is stable. Okay, how can we get it? If we put this term as greater than 0, okay, that means the system is stable. From there we can get the value for kp. If we put, as I told you, less than 0, then in that case whatever we got it for kp, that would be the unstable. If we put greater than equal to 0, then we'll get marginally stable. So you can note down this point. If we want to calculate kp, put greater than 0 for the stable. For marginally stable, put that equation equal to 0, and for unstable, put that equation less than 0. Now see, this is the question based on question 1 only, right? Now in this they said, consider the same hydraulic control system from question 1. The frequency response of the process transfer function g j omega as shown in figure 2.1, means we got gs was how much in the previous question, that is 10 divided by s plus 1 ka whole square, right? This was na gs. Now they said g j omega, correct? That means they have substituted the s for j omega. We can also do the same. G j omega is equal to 10 divided by j omega plus 1 ka square, correct? Now they said use it to verify the critical frequency of oscillation when kp is equal to k critical obtained in question 1. So again we have to do the same thing. Basically they are asking the value for kp, okay, and then that must be equal to k critical, means we need to do the same procedure again that we have already done in question 1. Okay, understood? Now in the second question they said sketch the root locus for the system, right? So for that we should know what we got it as gs hs, that we got it as how much, 10 kp s square plus 10s plus 40 divided by 10s s plus 1 ka whole square, right? That we solved now the transfer of gshs. That is not the transfer function, that is gshs only. We know the value of gs, we know hs, that is 1. Okay, now for basically for this one we have to plot the root locus. So what the very first step for the root locus, we have to determine the poles and zeros, correct? Now can you tell me how many are the poles in this case and how many are the zeros? See, how can we get the poles? Put that term is equal to 0. So 10s is equal to 0, we'll get s is equal to 0. Then put s plus 1 is equal to 0, then we'll get s is equal to minus 1. Again it's square, so minus 1. So these are the 3 poles present in this GSHS. Similarly, calculate the zeros for this case. See, this was the question of our root locus, right? We need to calculate GSHS was 10 kp s square plus 10s plus 40 divided by 10s s plus 1 ka whole square. From here we'll get the poles as s is equal to 0, minus 1, and we got zeros as minus 5 plus minus j 3.872, correct? You got the same? Now plot the graph, plot these poles and zeros on your graph of root locus. So if I'll draw the poles, based on poles and zeros. Based on this, then it would be 0, right? Suppose it is -1, so it would be -1, and we'll have a double pole, so marked it as a double pole like this. And then we'll have zeros at -5. -5 is something like there, and plus j 3.872 and minus j 3.872. So one of the 0 is here and another 0 is here. Okay, I'm drawing it again clearly. Like one of the pole is at 0, double pole at -1, right? Then 10 at -5 plus j 3.872, and another 0 it is at -5 minus j 3.872. Okay, understood? Now after this we need to calculate number of asymptotes, and number of asymptotes is p minus z. Poles are 3, zeros are 2, so it would be 1, right? So next we need to calculate angle of asymptotes. Angle of asymptotes formula is 180 into 2k plus 1 divided by p minus z, right? So from that we'll get asymptote as 180 degree. Now after that we need to calculate centroid. So centroid formula is summation of real part of poles minus summation of real part of zeros divided by p minus z. Okay, so centroid is denoted by sigma, as you already know. So summation of real part of poles minus summation of real part of zeros divided by p minus z. So real part of poles is 0, -1 and -1. Minus zeros are -5 plus j 3.872, right? Then -5 minus j 3.872 divided by p minus z is -2. Solve it and then tell me the value. So after calculating centroid, we got it as -8. Next step is to calculate breakaway point, right? Now how can we get the breakaway point? Take the characteristic, right? How will you get solve it? We'll take LCM 10 s into s plus 1 ka whole square plus 10 kp s square plus 10s plus 40 is equal to 0, right? So it would be 10 s s square plus 1 plus 2s plus 10 kp s square plus 10s plus 40 is equal to 0, right? Then 10s cube plus 10s plus 20s square plus 10 kp s square plus 10s plus 40 is equal to 0, right? So from here, if I'll shift it to the right hand side, then it would be equal to minus, right? Now I need to calculate the value of kp. So kp would be equal to 10 si. If I'll take common, then it would be s square plus 1 plus 2s divided by 10 s square plus 10s plus 40, right? Correct? So this 10 and this 10 would be cancelled out, right? So now we got this value as the KP. Okay. Now we need to differentiate KP. Like I'm writing again, the KP value is S divided by S into S square plus 1 plus 2S divided by S square plus 10S plus 40. Now we need to differentiate it with respect to S. Okay. Now remember, this is U by V. So we have to use differentiation rule, that is V du minus U dV divided by the square. Okay. So it would be S square plus 10S plus 40 the whole square, S square plus 10S plus 40, differentiation of this term, right? So it would be S cube plus S plus 2S square. If I'll solve it, then it would be S cube ka differentiation is 2S square plus S ka differentiation is 1, then 2S square differentiation is 4S, correct? Minus U dV as it is. So S cube plus S plus 2S square dV. Differentiation of V, that would be 2S plus 10, 40, differentiation is 0. Okay. Now any doubt up to here? Okay. So we'll get this one. This multiplied by 0 is 0. So what are we left with? We can open the bracket. S square 10S plus 40, then it would be 2S square plus 1 plus 4S minus, if I'll open this bracket, then it would be 2S4 plus 2S square plus 2 to the 4S cube, then I'll multiply it with 10, 10S cube plus 10S plus 20S square, right? Similarly, we need to open this bracket. After solving, we'll get the final value as S4 plus 20S cube plus 139S square plus 160S plus 40 is equal to 0. Now calculate the value for S.